welcome. We have been discussing the fluid equations and how fluids flow, and in the last class we derived the the three equations essentially that we use to determine the flow of fluids. So, we had first the continuity equation, and then we had Euler's equation, the Euler equation, and we had the energy equation. And in the situations, some of the situations that we are interested in, we also the fluid is self gravitating. So, the body force comes from its own gravitational potential, from the gravitation it generates on itself. So, F is minus grad phi, and that phi is governed by this equation, the Poisson equation. It tells you how the matter, the fluid itself produces a gravitational field. Okay. So, these are the fluid equations, and today's class we shall consider a few examples of solutions and implications of the fluid equation. So, let us start off with the simplest possibility, which is hydrostatics. Okay. So, we shall discuss hydrostatics first. And what we mean by this is that the fluid is at rest. So, there are no time derivatives, and the velocity of the fluid is also 0. Okay. So, all time derivatives vanish and the velocity is also 0. So, under this condition, the continuity equation is trivially satisfied because all time derivatives vanish and the velocity is 0. The Euler equation, the first two terms involving the velocity do not contribute, and we have essentially grad P is equal to rho into the force per unit mass or the acceleration. So, that is the first equation. That is the Euler equation. So, the two forces, the pressure gradient force and the body force, they have to cancel out. And the energy equation, again the time derivative is 0, the velocities are 0. So, it tells us that the heat loss, the rate at which the heat is lost has to be 0. So, hydrostatics, we have two very simple equations which have to be satisfied. Let us consider a few examples now of hydrostatic equilibrium, where we have a fluid which is in hydrostatic equilibrium. So, let us first consider a fluid which has a uniform density more or less, and same temperature also. So, like water, so this is, so let us say it is incompressible and the temperature isothermal. Temperature is also the same throughout. So, the example is a tank full of water or some fluid like water, which is nearly incompressible, okay, at the for the purposes at least here. And this is the z direction. Let us say that choose the z direction upwards. Let us call this the z direction, and this is z equal to 0, and the pressure here let us say is P naught. Okay. So, so we have this equation. It now, since the temperature is the same throughout, there will be no heat loss from one part of the fluid to another. So, we did not bother about this. Let us look at this equation. This equation tells us that dP dz is equal to, now we have the density of the fluid and this is the force per unit mass, the body force, and in this case it is just the gravitational acceleration. So, this is minus, it acts downwards, the force acts downwards, gravitational acceleration. So, minus rho into g along the z axis. Okay. And the solution to this is straightforward. So, we have P is equal to P naught minus rho g z, right. So, as you go up, the pressure keeps on falling, or there you may say that there is a pressure due to the column of the fluid above the particular point that you are looking at. Okay, this is a very simple application of the fluid equations, hydrostatic. Next, let us consider the same thing. Now, let us consider a gas, an ideal gas which is isothermal. So, you can think of it an ideal gas. So, it is isothermal at the same temperature, and we have an ideal gas. So, the same thing, there is the gravitational force acceleration, and we can assume that the gravitational acceleration does not change. Okay. So, an example of this application of this could be the surface of the earth, and we are interested in how the there is the atmosphere, earth's atmosphere. So, we are interested how the pressure of the atmosphere changes as we go up along the z direction. Again, let us take the z equal to 0 over here at the surface of the earth. Okay. And so, we are not concerned with the change in the gravitational acceleration. So, our distance, that the distances that we are interested in are relatively small compared to the radius of the earth. Okay. So, few kilometers. So, suppose I go from here to the top of Mount Everest, my height will change by roughly 10 kilometers, not less than 10 kilometers. Okay. And the radius of the earth is, so let us assume that the gravitational acceleration is more or less same. Temperature also, let us assume that it is more or less same, though we know that the top of Mount Everest is going to be much cooler. But let us make some simplifying assumptions like this and go ahead and see what happens if you assume that the whole atmosphere is in hydrostatic equilibrium. So, again, since the temperature is the same everywhere, there will be no heat loss from individual fluid elements. So, the heat loss is 0, and we have dP dz is equal to minus rho into g. Okay. dP dz is equal to minus rho into g, right. That is the first equation. But now we know that this is an ideal gas. For an ideal gas, we also have that the pressure is PV is equal to N kB T. Pressure into the volume of the fluid is equal to the number of atoms or molecules in the fluid into the Boltzmann constant Kb into the temperature in Kelvin, absolute temperature. Okay, that is the relation between the pressure, volume and the temperature for an ideal gas. PV is equal to N kT. Okay. N is the total number of, or we can use capital N for this, okay, total number of atoms or molecules in the system, okay, particles. Now, this we can write as P is equal to, so I can divide N by V. multiply by the mass of each particle n by V kb T, and I have to divide by the mass of each particle. So, we have the pressure is equal to, this we know is the density, mass into number of particles divided by volume. So, it is rho kb T by m. Okay. So, with this relation between the pressure and the density, they are not independent now. Temperature is the same throughout the atmosphere. So, this is the atmosphere we are dealing with. The atmosphere we are dealing with is here, and the temperature is the same throughout. So, this equation now becomes d rho dt is equal to, so let me put all the factors on the right hand side. We have minus mg by kb T into rho. D rho dz, sorry, d rho dz, sorry, it is a dz derivative. D rho dz is equal to this. Okay. So, now we can integrate this, integrating this is straightforward. We have d rho dz is equal to a constant minus constant into rho. So, the integral of this is straightforward, and what we have is that rho is equal to some rho naught exponential minus m g z by k b T. Okay. And you can check it for yourself in general, that if the body force is the gradient of a potential minus the gradient of a potential acceleration, then we can write this as rho naught or you okay, you can check this that it comes out to be this, where f okay. So, if the acceleration f, which we have here assumed to be constant, is the gradient of some potential, then it can in general be written like this. Okay, this I have not shown, but you can check it for yourself. Okay. So, what do we see over here? What we find is that if you assume that the atmosphere has a constant temperature and the gravitational field is a constant as you go up, then the density of the air falls exponentially with the height, and the density falls exponentially implies that the pressure also falls exponentially with height. So, this gives you a reasonable approximation of how the density of air and the pressure decrease as you go up above the earth's surface. Okay. And the pressure and the density, for example, on the top of Mount Everest are considerably lower than what they are here, which is why people require oxygen, and you would be severely sick if you were there in at altitudes greater than 7,000 6,000 meters for considerably long time. Okay. So, you have different kind of mountain sickness, altitude sickness arising from this. Okay. So, we have considered two examples of hydrostatic equilibrium. Let us consider a third example, which is astrophysical in nature. The third example of hydrostatic equilibrium, where we apply this concept of hydrostatic equilibrium, is the solar corona. So, let us take a look at what we mean by the solar corona first. The solar corona, so this is a picture of the sun taken during the 1999 total solar eclipse, and the sun here is blocked out by the moon. Okay, I have shown you this picture already. Now, the interesting thing here is that when the sun is blocked out when the sun, the dazzling light from the sun is blocked out, then you see this very faint and tenuous bright thing around the sun. This is called the corona. It comes from the word crown. Okay. So, it surrounds the sun, and the radiation from this is 1,000,000 times fainter than the radiation from the sun. The radiation from the sun originates in the photosphere. So, it is 1,000,000 times fainter. So, you can only see this in the visual light if the sun is blocked out, which happens during a total solar eclipse. So, the corona is seen only during a total solar eclipse. Okay. That is the first thing. But if instead you were to make an X-ray picture, X-ray image of the sun, this shows you an X-ray image of the sun taken from a Japanese X-ray satellite. Now, in this image, okay, in this image what you notice is that the sun is darker and the corona which is outside the sun is actually brighter. Okay. So, in X-ray you do not need a solar eclipse to see the corona. You can see the sun even otherwise, when in any X-ray image of the sun, it is the corona which is brighter than the sun itself. Okay. Now, that is very surprising, but it is a fact. Okay. So, the solar corona is extremely tenuous, the density is very low. Okay. Hot gas, hot plasma essentially, it is ionized. By plasma we mean ionized gas. So, there is an extremely low density and extremely hot plasma surrounding the sun. Okay, that is called the solar corona. And in visual the radiation is 1,000,000 times fainter, but in X-ray it is brighter. The temperature at around 1.2 solar radius, these are rough values, is around 1.4 million Kelvin. Okay. And the density is around 200 million electron number density is 200 million particles per cc. Okay. And it is mainly electrons and protons, some amount of helium ions also, but mainly helium, hydrogen, electrons and protons, hydrogen ions. Okay. So, the sun is surrounded by this very hot, very low density plasma around the sun, which surprisingly is much hotter than the sun. Okay. And it is a very puzzling matter. How is this solar corona, which is around more than 1,000,000 Kelvin, how is it hotter than the surface of the sun, which is just 5,800 Kelvin? Okay. What maintains the corona at a higher temperature? It's rather puzzling issue. Okay. It is okay. So, it is now believed that it is possibly originating from small patches of magnetic fields that are found all over the sun. Okay. So, the source of the energy is now believed to be small patches of magnetic field found all over the sun, and possibly if you look at the pictures of the sun, I have shown you one right in the beginning, you have these solar flares, these are gas which come out from the sun. Okay. So, you have these solar flares also coming out. Now, it is widely believed, accepted that the corona is heated by magnetic fields. Okay. So, when the magnetic fields come out of the sun, these magnetic fields are carried by the motion of the plasma. Now, when the magnetic fields get intertwined, then what happens? They reconnect. So, you may have, by the motion of the plasma, a very complicated pattern of the magnetic fields. Then they reconnect, so that you have simple patterns, and some magnetic field blob may just separate out, and during this reconnection energy is pumped in to the plasma outside the sun. Okay. That is the picture. So, the flares also do carry out energy from the sun, but it is now believed that these solar flares, which are seen only during the active period of the sun and they do not occur during the passive period of the sun has these periods. So, they are not the source is possibly these small patches of magnetic field. Anyway, it is the general picture is that it is transmitted to the plasma through magnetic forces, which the reconnection of magnetic fields, but it still remains an unsolved issue. Okay. For our purposes, let us not bother about it. Let us not bother about what heats the solar corona. What we are concerned with is as follows. So, let us try to model the solar corona. So, we are going to try make a model for the solar corona. So, this is the surface of the sun, and at the radius of the sun r naught, we will assume that it has some temperature, very high temperature T naught, okay, and it has some pressure P naught, and you can then work out the density. Okay. Further, we will assume that it is in hydrostatic equilibrium. So, this gas outside the sun, we will assume the plasma is in hydrostatic equilibrium, and as r goes to infinity, we expect the temperature to go to 0, the pressure to go to 0, and everything vanishes, right. So, this is a gas which is there in hydrostatic equilibrium. There is a temperature T naught which is very high, which is maintained by the sun at the center, and the temperature falls off as you go far away. At infinity it should be 0, the pressure should also be 0. That is the model which was worked out by Parker, okay, famous plasma physicist at the University of Chicago called Parker. He worked out this model. Now, so let us go back to our equations of our hydrostatic equation. So, these are the two equations that we have, and the first equation, here everything varies only in the radial direction r. So, the first equation is that the radial derivative of the pressure del P del R is equal to, we have the density into the force, the body force. So, the body force here is acting inwards. So, we have equal to rho. Now, let us write rho in terms of the pressure. So, we know that if you write rho in terms of the pressure, we have worked it out in the last example. So, we can just write rho in terms of pressure. So, this will be mp by kb T. So, we have mass of the particles by P by kb T, and then we have the gravitational force. The gravitational force is minus g m by r square. So, so we have this, that is the first equation. We also have the condition that the heat loss L should be equal to 0 for any unit of the fluid, any unit per unit volume of the fluid should be 0. Let us consider the heat loss first. Okay. Now, if you have a fluid, okay, this is a fluid, let us say, whose different parts are at different temperature, or anything like any medium where different parts are at different temperature, we know that heat will flow from the hotter to the cooler part through conduction, okay. And the conduction current. So, the conduction current that flows out from this, let us just consider this is at a temperature T1, this is at a temperature T2, slightly different, okay. The conduction current that flows out from this is J, it is proportional to the rate at which the temperature changes with position, right. So, the conduction current is minus K grad the temperature, right. This is the temperature difference. Then you have a conduction current, and if it is in opposite direction as the temperature gradient, right. And this K is the heat conductivity, which is dependent on the material. So, that is the conduction current. And if I now have a unit small volume here and ask what is the total heat that flows out, then you have to take this current and do a surface integral over this, and the surface integral can be converted into a volume integral through Gauss theorem. So, we know that the heat loss rate is essentially the divergence of the conduction current, right. That is the rate at which the heat is flowing out. So, in this case, different parts of the solar corona, the temperature is going to be hottest near the surface, and then the temperature is expected to fall off. So, we are going to have heat conduction, and we will have a current, but the total heat loss per unit volume should be 0. So, it is essentially what it tells us is that in spherical polar coordinates that so the condition is that del, let me first write down the condition, del dot K grad temperature, this should be equal to 0. Okay. So, this is the condition. Further, we also know, it is known, okay, I am not going to go through it here, it is known that the heat conductivity in a plasma K is proportional to T to the power 5/2. It increases with temperature. The hotter the plasma, the better it conducts heat. Okay. So, this is known. So, what it tells us for our problem is that this in spherical polar coordinates, this becomes d by dr r square t to the power 5/2 d by dr t is equal to 0. Okay. Or what it tells us, or we can write this as follows, we can write this as d by dr d by d of 1/r. So, if you do the d by d of 1/r, then you will get r square by dr with a negative sign, that does not matter because it is equal to 0. So, d by d of 1/r of t to the power 7/2 is a constant, right. This is what it tells us. This equation will give us this, is a solution to this. So, the fact that the energy equation here finally tells us that the temperature scales. So, I can write down the form of the temperature over here. So, what it tells us is that the temperature T is equal to scales as r to the power minus 7 by 2, right, 1 by r and right r to the power minus 7 by 2. So, so let me put it here. This implies that the temperature varies with r as equal to T naught r naught by r this should be 2 by 7, sorry, not 7 by 2, right, 2 by, right, this T to the power 7 by 2 is equal to this. So, this should be 2 by 7. Let me just write down the solution here. Okay. Now, we have to next use this in this equation. We now know the temperature. So, we have to put this into the equation for the pressure. So, let us do that. So, let me do that next. So, the Euler equation, what it tells us is that dP dr is equal to, let me put all the factors correctly. So, we have m, we have a minus sign, and then we have g capital M small m, g capital M small m, and here we have kb r square by kb T. Okay, the temperature we will write as T naught. So, T naught, and we have r square here, and then I will write r naught to the power 2 by 7 and r to the power 2 by 7. So, here I have r naught to the power 2 by 7. In the numerator I have r to the power of 2 by 7 and then we have the pressure itself. So, we can now integrate this equation. If I integrate this equation, what I will get is d ln p is equal to, and I have to integrate this term now. Now, this term, let us see what the we have g m m by k b T naught and what is the combined r dependence of this term? Let us see. So, the combined r dependence of this term is r to the power of minus 12 by 7, r to the power of minus 12 by 7. This is 14 by 7, this is 2 by 7. So, it is r to the power of minus 12 by 7, and if I integrate r to the power of minus 12 by 7, then I will get 5 by 7. So, I will have 7/5 here and I will have r to the power of minus 5 by 7. So, I have r naught to the power of 2 by 7 and r to the power of 5 by 7. which we can write the solution straight away now. P is equal to, so there will be a constant when I integrate this, which I can write as P naught, absorbing everything, exponential, I can write this whole thing as follows, exponential, then I have 7/5 G m m by K b T naught and so we have r to the power of 5/7 here. So let me write it as r to the power okay. So what we can do is we can write this as r naught over here. So I can write it like this, r naught by r to the power 5/7 minus 1 into this factor. Okay. This minus 1 into this is a constant which I can which will just multiply P naught and it will give me the constant of integration here. So the pressure can be written like this, that is the solution to this. Okay. Now the point to note over here is that if you at r equal to r naught, this gives me exactly P equal to P naught. Okay. Here we have put the boundary condition that the temperature goes to 0 as r goes to infinity. We have imposed the boundary condition that the temperature goes to 0 as r goes to infinity. Okay. So this ensures that T goes to 0 at r tends to infinity. Okay. Now we would also like the pressure to go to 0 as r goes to infinity, but notice here that at r equal to infinity the pressure does not vanish. You have a finite value for the pressure. Okay. And this pressure turns out to be more than the pressure of the interstellar medium. So between the stars there is some gas. So if this pressure were equal to that pressure of the interstellar medium, then we could say that they are in equilibrium over there, but this pressure turns out to be considerably more than the pressure of the interstellar medium. So what Parker showed was that you cannot have a static solution. If you want the where the temperature and pressure both go to and the density everything goes to 0 at infinite. So if you want to hold the solar corona in place in hydrostatic equilibrium, then there must be something exerting pressure at infinity. And we know that there is no such thing exerting pressure at infinity. So he concluded that the solar corona must be expanding out. Okay. So this is the proposal made by Parker in 1958 based on this simple calculation. And initially this calculation was not accepted, his paper was actually rejected from AFJ by 2 referees. Fortunately Chandrasekhar was the editor and he accepted it. But this proposal was verified by a Soviet satellite in 1960, satellite Luna 1. Okay, and now it is well known that there is a solar wind. So the gas coming out, this gas outside the sun is not in hydrostatic equilibrium, it is actually blowing out. Okay, and it is mainly made up of electrons and protons like the corona. Now at the location of the earth, near the location of the earth, the number density is around 3 to 10 particles per cc, considerably smaller. The flow speeds are of the order of 400 kilometers per second and the temperature is around 150,000 Kelvin. Okay. There are occasional streams which have 750 kilometers per second speed, and there are impulse events which can have speeds as high as 1000 kilometers per second. Okay. Solar winds are very important for satellite communication, and they can also have measurable effects on the flight paths of spacecrafts. It is a wind, constant wind blowing out from the sun. Okay. And this shows you a picture, not a real picture, it is an artist's impression of the solar wind. So, this is the sun at the center of this picture, and this is the heliosphere. This is the region which is filled up by the solar wind, and here it is actually interacting with the interstellar medium, and you have this Bohr shock, and this whole thing is the heliosphere up to here. And this also shows you the trajectory, the path of Voyager. So, the Voyager is the satellite, human man built satellite that has covered the largest distance till now. So, it is still within the solar wind. Okay. To put this in scale, this picture shows you the same thing, and you can see that the solar wind extends to hundreds of astronomical units. Okay. Now, let us get back to what we were doing. We were discussing fluid mechanics, and we just took a diversion and discussed the solar corona, one astrophysical application, and its consequence, the solar wind. Okay. The solar wind can also be described in fluid mechanics terms. Maybe we shall discuss it later on in this course. So, let us get back to what we were discussing. So, we were discussing the fluid equations, and we until now have discussed the hydrostatic situation. Let us now go back to the fluid equations and apply it to flows, okay, where there are velocities. The situation that we considered till now, there were no velocities. Let us now go and look at fluid flows. So, before we start discussing flows, let me briefly discuss the nature of the velocity field. Velocity field V. Now, it is a well known fact in vector calculus that this vector field V can be decomposed into two parts. One part which has a divergence, this has a divergence, and another part which has only a curl. This is called the vorticity. Okay, this is usually denoted by omega, the curl of V, and it is called the vorticity. And what do these two represent? So, we know from Gauss theorem that del dot V, so the divergence, if the divergence is positive, it tells us that if this is my volume, it tells us that the fluid is flowing out. A vector field which looks like this will have positive divergence, right. And the opposite situation where it is converging will have negative divergence. That is simple application of Gauss theorem. This can be converted into a surface integral, and if you take an infinitesimal volume, it tells us the flux out of that volume or into that volume. Okay, so the divergence represents this kind of a motion. Okay. Now, we also know the Stokes theorem. The Stokes theorem tells us that take V dot dl around a closed loop in the anticlockwise direction. So, this is a loop, take a closed loop like this and integrate V dot dl around such a loop. So, dl is the tangent vector to the curve. So, you integrate this V dot dl, and from Stokes theorem this is equal to the surface integral of curl of V dot ds. Okay, so ds is now pointing inwards. No, ds is pointing inwards. Sorry, this is clockwise. I have drawn the picture incorrectly. It should be other way around, anti-clockwise. Right. Now ds points outwards, and you take the curl of v and do dot ds and integrate over this. Then you, if whatever it gives you is essentially the circulation, the v dot dl. So a velocity pattern that looks like this, goes around in a circle, okay, is what is quantified by the vorticity, the circular motion. It is also called circulation. This is also called circulation. Okay. So this is vorticity, and this integral is also called circulation, the surface integral of the vorticity. So if so the velocity field can be uniquely broken up into these two parts, a part that has a divergence and a part that has a vorticity, the curl. And conversely, if I told you these two components, you could reconstruct the entire vector field. Okay. So if I told you what the divergence was and what the curl vorticity is, if I tell you these two components, you can reconstruct V. Okay, these are all well known things in vector calculus. Now let us go back to the Euler equation. So this is the Euler equation, and it is often convenient to write it in a slightly different way. So let me do that. So we will use the vector identity that okay. So you can use the identities relating A cross B cross C, which you all know. Okay. So you can use this to simplify this expression, and if you do that, what you will find is that you can write this as the gradient of half V square. Okay. So just A cross B cross C, nothing more. Okay. Apply that identity. So this turns out to be a gradient of half V square minus V and this is the term that appears in the Euler equation. So we can replace this in the Euler equation, and what we have now is so that is the Euler equation written in a slightly different way. Okay. Now let us, we can do a few things using this. So let us look at flows. So, let us consider steady flows. What do we mean by a steady flow? A steady flow is a situation where we have a velocity and we have a density, but everything is time independent. Okay. Now, for steady flows you can define something called a streamline, streamlines. Okay, these are curves the tangent to which denotes the direction of the flow. So, the velocity, the tangent to which the velocity at any point is the tangent to this curve. Okay. And you can think of it like the electric field or magnetic field, these are also some field lines. The velocity field at any instant is a tangent, at any position is a tangent to these curves, these are called streamlines. Okay, and the fluid flows along, actually flows along these streamlines. Let us now integrate this equation. Okay, so, we are considering a steady flow, so there is no del V del T. Let us integrate this equation along a streamline. So, we are going to integrate this equation along a streamline. Okay. And let me write it down. Okay, before we write down, let us just look at this term. If I integrate this along a streamline, then so okay, let me write down the term. So, we have V cross curl of V dot this dot dl, where dl is a unit infinitesimal vector along this direction, right. That is what we mean by integrating along a streamline. Now, dl is parallel to V at this point, this is V cross something. So, it is obvious that this is going to be 0, this does not contribute. Okay. So, what we are left with is basically the integral of this, the other 3 terms. So, what we have is that the integral gradient of half V square plus grad P by rho minus F. Now, we are going to also assume that the body force F, acceleration force per unit mass, can be written as the gradient of some potential. Okay. So, we are going to assume that F is equal to minus grad phi. Okay. Could be gravity, could be electric field, something. Okay. So, then this becomes plus grad phi dot dl is equal to 0. Now, these 2 terms are gradients. So, the dot dl is essentially just the difference between phi's, the velocity and the phi. So, this tells us that so, when I integrate this, I will get just the constant, I will just get the value of half V square plus phi at this value minus the value of half V square plus phi at this value. So, what we can say from this is that this plus the integral grad P by rho dot dl should be a constant, and this is what is known as Bernoulli's theorem. And if your fluid happens to be incompressible, the density is the same throughout, then it simplifies even further. What it tells us is that half v square plus phi plus p by rho is a constant. Okay, which is Bernoulli's theorem. Let us work out one quick application of the Bernoulli's theorem before we end today's lecture. So, we have a container like this with a small outlet over here, and let us say the outlet points upwards, and it is filled with some fluid. So, the fluid is going to obviously flow out, and it is going to flow out something like this, and then it will fall. And let us say that this difference in height is h, and as the fluid flows out, the height, this width is so large, let us assume that the water level here does not fall very appreciably. Okay, and we would like to calculate the velocity of the fluid at this point. So, the velocity here is 0, the pressure, atmospheric pressure is P naught. Let us apply this equation. So, at the top of the fluid at the point A, the velocity is 0, there is a gravitational potential which is mg, h, gravitational potential is gh, okay, and we have the atmospheric pressure by rho. So, g h plus P atmospheric pressure by rho, this should be equal to, now at the outlet over here at the tip of the outlet, we have half v square, this is the height difference, sorry, between the tip of the outlet and this. Okay. At the tip of the outlet, we have half v square, this is equal to half v square plus phi, so the potential is 0, plus P naught by rho, right. So, what we see is that these two terms cancel out, and what we get is that V is equal to the square root of 2g h. Okay. So, we have used Bernoulli's theorem to calculate the speed with which the water comes out of the outlet over there. Okay. So, let me end our discussion of fluid mechanics over here, and we shall move on to some other topic in the next class. And what we mean by this is that the fluid is at rest, so there are no time derivatives, and the velocity of the fluid is also 0. Okay. So, all time derivatives vanish and the velocity is also 0. So, under this condition, the continuity equation is trivially satisfied because all time derivatives vanish and the velocity is 0. The Euler equation, the first two terms involving the velocity do not contribute, and we have essentially grad P is equal to rho into the force per unit mass or the acceleration. So, that is the first equation. That is the Euler equation. So, the two forces, the pressure gradient force and the body force, they have to cancel out. And the energy equation, again the time derivative is 0, the velocities are 0. So, it tells us that the heat loss, the rate at which the heat is lost has to be 0. So, hydrostatics, we have two very simple equations which have to be satisfied. Let us consider a few examples now of hydrostatic equilibrium, where we have a fluid which is in hydrostatic equilibrium. So, let us first consider a fluid which has a uniform density more or less, and same temperature also. So, like water, so this is, so let us say it is incompressible and the temperature isothermal. Temperature is also the same throughout. So, an example is a tank full of water or some fluid like water, which is nearly incompressible, okay, at the for the purposes at least here. And this is the z direction. Let us say that choose the z direction upwards. Let us call this the z direction, and this is z equal to 0. And the pressure here, let us say, is P naught. Okay. So, we have this equation. It now, since the temperature is the same throughout, there will be no heat loss from one part of the fluid to another. So, we did not bother about this. Let us look at this equation. This equation tells us that dP dz is equal to, now we have the density of the fluid and this is the force per unit mass, the body force, and in this case it is just the gravitational acceleration. So, this is minus, it acts downwards, the force acts downwards, gravitational acceleration. So, minus rho into g along the z axis. Okay. And the solution to this is straightforward. So, we have P is equal to P naught minus rho g z, right. So, as you go up, the pressure keeps on falling, or there you may say that there is a pressure due to the column of the fluid above the particular point that you are looking at. Okay, this is a very simple application of the fluid equations, hydrostatic. Next, let us consider the same thing. Now, let us consider a gas, an ideal gas which is isothermal. So, you can think of it an ideal gas. So, it is isothermal at the same temperature, and we have an ideal gas. So, the same thing, there is the gravitational force acceleration, and we can assume that the gravitational acceleration does not change. Okay. So, an example of this application of this could be the surface of the earth, and we are interested in how the there is the atmosphere, earth's atmosphere. So, we are interested we have been discussing the fluid equations and how fluids flow, and in the last class we derived the the three equations essentially that we use to determine the flow of fluids. So, we had first the continuity equation, and then we had Euler's equation, the Euler equation, and we had the energy equation. And in the situations, some of the situations that we are interested in, we also, the fluid is self gravitating. So, the body force comes from its own gravitational potential, from the gravitation it generates on itself. So, F is minus grad phi, and that phi is governed by this equation, the Poisson equation. It tells you how the matter, the fluid itself produces a gravitational field. Okay. So, these are the fluid equations, and today's class we shall consider a few examples of solutions and implications of the fluid equation. So, let us start off with the simplest possibility, which is hydrostatics. Okay. So, we shall discuss hydrostatics first. How the pressure of the atmosphere changes as we go up along the z direction. Again, let us take the z equal to 0 over here at the surface of the earth. Okay. And so, we are not concerned with the change in the gravitational acceleration. So, our distance, the distances that we are interested in are relatively small compared to the radius of the earth. Okay. So, few kilometers. So, suppose I go from here to the top of Mount Everest, my height will change by roughly 10 kilometers, not less than 10 kilometers. Okay. And the radius of the earth is, so let us assume that the gravitational acceleration is more or less same. Temperature also, let us assume that it is more or less same, though we know that the top of Mount Everest is going to be much cooler. But let us make some simplifying assumptions like this and go ahead and see what happens if you assume that the whole atmosphere is in hydrostatic equilibrium. So, again, since the temperature is the same everywhere, there will be no heat loss from individual fluid elements. So, the heat loss is 0, and we have dP dz is equal to minus rho into g. Okay. dP dz is equal to minus rho into g, right. That is the first equation. But now we know that this is an ideal gas. For an ideal gas, we also have that the pressure is PV is equal to